My hairline is not going back, right? I just wanted to know and ask you guys. Anyways, welcome back to my series, guys. It's day 43 of my algorithm challenge. Today, we're still gonna explore dynamic programming. This should be our last exercise that we do in this topic. Of course, we're gonna go back to all the templates that we have done so far, from sliding windows, hash maps, all that kind of greedy algorithms, all that kind of stuff. But yeah, to do that, we're just gonna finish off this. Um, so yeah, I'll also make sure that I have like a good eye target because I've had the feedback that my eye is rolling constantly sideways. So um, I'm trying to fix that. So yeah, let's see. I'm gonna I'm gonna share my screen and hopefully it works in my first try, and seems like it does. Okay. Today's question is unique paths. It's a medium level difficulty question. It was showcased in Google and Microsoft interviews. So there's a robot on a m times n grid. Actually, we've used this approach where the state variable is a matrix yesterday, right? When we were doing, I don't remember what we were doing, but we were definitely using the grid. But we're showing the solid case of using grids. So the robot is initially located in top left corner, and we try to reach to the bottom right corner, and it can only move either down or right at any point of time. So given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. So let's see. What do we need? What did we say that we need in order to solve the dynamic programming question? Now I can just remember from my heart. First one is state variables. Second one is recurrence relation. And third one is the base case, right? So what will be the state variable in this case? Well, that's simple, right? It's just a grid. So it's just row and column. So which row this robot is in and which column it is in right now. Um, so we have to define the dp of row and col as the number of unique paths to reach the cell at the position row col from the start, which is 0 and 0, right? Because it is at 0 and 0. Let's see, Python. So the state is dp row and column. Now, what do we need? We also need a recurrence relation, right? The state transition. So to determine the number of unique paths to reach the cell row and column, um, we have to consider how we could have arrived to that cell. So this could be done in either two ways. First, from the I'm just writing it as if it's a Word document, so please don't mind me. From the left, the cell immediately to the left is row column -1. So given a position, the cell right next to it, right to the left, is column -1, right? That makes sense because column is here and then you just -1. So and also from above, you can just come from above as well, right? To reach that row column cell. So that will be from uh in this case row -1, right? So because we're just coming from row -1 to row and column. So now the unique number of paths to reach the cell row and column is the sum of the unique paths to reach the cells directly above it and to the left of it, which comes down to dp row col is dp row minus 1 col plus these two cases, right? Row col minus 1. So that makes sense. So this relation works as long as we're in the bound variable. So what that means is uh, because for these grid, we have defined that the robot is not going to go below 0, right? So it can never be -1 or -2 or -3. So we just have to state that as long as row and column is more than 0, then this recurrence relation will work. So actually, that was pretty simple for a recurrence relation, right? Better than yesterday, where there were we were going through indexes. Okay, lastly, we need to define the base case. So how would we define the base case? So the base case occurs when at the starting point at 0, 0, where there is exactly one way to be at the start when you start there. So that's when you're at 0 and 0, right? So so in that case, dp 0 and 0 equals to 1. So for the first row and the first column, there's only one way to reach each cell. So that's either by moving right from the start. So that's for the first row, or by moving down from the start. So that's for the first column. So therefore, dp 0 and j, let's call it as j, equals to 1 for all j in the first row, because it will stay the j when it's in the first row, and contrary to this, when dpi 0 is 1 for all I in the first column. Because when it's 1, it cannot move up when the column is 0 index, and when the row is 0 index, then we cannot move left. Actually, it's the other way around. When the column is 0 index, we cannot move left, and when this row is 0 index, we cannot move up. So we have to define that as a base case. So the final solution, if we just compile this all together, let's see. So we define the dp row and column. And now, if row plus column is equal to 0, then we return 1, which is the base case, right? And we have to keep track of the number of the ways, right? So let's put that as paths equals 0. And if row is equal to 0, then paths plus the dp of, we're doing this by top-down approach, by the way, guys, of the recurrence relation, which is row minus 1 and column. And if column is equal to 0, then it's the other way around, paths plus dp row and column minus 1, right? Now we return the number of paths, and finally return the helper function, which is return dp. Because in the description we said we have to reach the bottom right corner, which is m-1 and m-1. So we have to respect that, m-1, m-1. So let's try to run this. Let's see if it works. Oh, worked in the first try. Okay, so guys, that was it for Matrix. Actually, more and more I solve this dynamic programming questions, I feel like um, it's really easy to use top-down approach rather than using bottom-up approach. Because initially when I saw uh, the both approaches, because I saw that you use a for loop in bottom-up, it'll be way easier, but turns out it wasn't. So, well, it is what it is. But that was it for dynamic programming, guys. I think tomorrow maybe we'll take some time to look at all the templates and have some time to re-recognize those templates. But yeah, thanks for watching this and see you guys all tomorrow.